So then how do we show that something is a subring? What is the definition for the subring?
Those are the addition, multiplication, and inverse.
So we have to show that B is closed. What was the first thing you said? Addition?
Addition.
Okay. So we have to start with what? 2 elements in B, right? No. What do you mean? No, assume, well, it says assume that B is closed with respect to subtraction. That's not the same thing as addition.
Oh.
Yeah, I have to show that A plus B is in B. Yeah. How do I get to an A plus B when I know something about subtraction? Yeah, but I have almost A minus a negative B, right?
Oh.
Right? That's one of our rules from groups. When you have the additive inverse of the additive inverse, you have the original value.
So it doesn't matter that we don't know that it's closed with respect to the inverses yet. We can use an inverse.
I didn't say that this is in B yet. We have to show it. Yeah.
Okay, it says that B is closed with respect to subtraction and multiplication, and then in the book it says the definition for it being a subring is that it's that. So do you really have to show
No,
it?
the definition for subring is on the first page. This is a theorem. It's like the shortcut rule for proving subrings. The very first page definition for
It says the
subring.
addition, multiplication, and negative.
Yeah.
And then it says right here, if and only if it is closed on addition and negative.
Yeah, we're just proving that that's
We're
true.
proving that if and only if statement that they gave us. If you notice what it says at the end of that paragraph, it says, this last fact is easy to check and is given as an exercise.
Okay.
So we're proving the hard way. The other way is really straightforward. If it is closed, you got a subring. Yeah. I mean, if it is a subring, you've got those properties. So we're going the other direction on it, so we have to show this. But to be able to claim that this is in B, we have to know something, right? If we know minus B is in B and I know A is in B, then by hypothesis A minus B will be in B, right? So we would like to know that minus B is in B. How do we get minus B to B? Well, that's not so hard. Let's go back up to right here. We'll put a couple of returns and we'll come in. Now we're going to go get our minus B to be in B. Note that the additive identity we're calling 0 from A has to be equal to what? Oh, yeah, I didn't ask the question correct. In terms of our element B, in our set B, what can we do to B to get to the additive identity? Subtract it, right? B minus B? Yeah. Note that 0, the additive identity in A is equal to B minus B. So where does that tell you that the additive identity is going to live? It has to be in B, since B is closed with respect to subtraction. B minus B lives in B, since B is closed with respect to subtraction. Now, tell me something else. What could I add to a minus B to show that minus B was in B? Why? B is closed under subtraction, right? I know 0 mod is 0, the identity is in B, and B is in B, so negative B has to be in B. So now that we have negative B in B, what can we conclude? Yeah, I'm going to take this out of here. Now we can look at A plus B, which is a minus B, lives in B because B is closed with respect to subtraction. So I know that A plus B is in B. What's our conclusion for that little part? Therefore, B is closed with respect to what? Okay, second thing that we need to show. Which question? They're arbitrary. I didn't choose anything particular about those values. So for any two values from B, I can arrive at that conclusion. So it has to work for every two values I choose. No, I used a 0 to be able to show that minus B was in here. I needed to be able to add, to subtract something, but not lose my minus B. I need to be able to say minus B equals the difference of two values. And I know that when I choose 0 to be one of those values, then minus B equals 0 minus B. Yeah. So if I have to show that 0 is in B, to be able to show that minus B is in B, because I know B itself is in our set. And the difference of any two elements in the set is in the set. That was our hypothesis. Make sense? So I just showed that A plus B, because I can write it as A minus B, is in B. Tricky, yes, very tricky. What else do we have to show for a subring?
Didn't you just show that closed with respect to inverses?
Say that one more time.
Does that top stuff not show that it's closed with respect to inverses?
It shows that it's closed with respect to negatives.
Oh, yeah.
Yeah, and that's what we're talking about, right? Chapter 18.
Oh, are they not the same thing?
Let's see, we have to show what closed with respect to negatives, which isn't quite the same as inverses now because inverses could be multiplicative. So inverses aren't just additive, they're... So we could go up here and write down right here. It follows that B is closed with respect to negatives, right? Now, what's the last thing we have to show? Multiplication. But isn't that by hypothesis? I can't spell multiplication today. Draw your conclusions. Therefore, B is a subring of our ring A. That makes sense? That's the long way. You actually have to verify three things. But the rule that we kind of sort of proved here is if you know that B is closed with respect to subtraction, for any two elements, A and B, if you know that A minus B is in B, and you know multiplication, then you know B is a subring. So you just have to verify two things now in your homework. So that was the first thing that they kind of left open. I have, I fixed the numbering here. There we go. I have put a little proof in here. This is kind of an aside that you need for the next proof that you're going to be looking at. It says let F take A to B be a homomorphism of a ring A to a ring B. Show that F of minus X equals minus F of X for all X and A. So how did I do this? Very similar to how we've looked at it before.
You know you have a homomorphism. What we're going to do is write down the additive properties for it. And you have f of x plus f of minus x. I'm just trying to write down the additive inverse kind of ideas here. So f of x plus f of minus x is equal to f of x minus x, right? Applying homomorphism. But what is x minus x? The identity. And it's in fact the zero identity. So that's f of the zero identity. But when we proved homomorphisms for the additive properties for groups, we said that it preserves the identity. So I know that has to be the additive identity in B. You go back through and switch the order on it, and you'll see that you get the additive identity in B again. So your conclusion is that minus f of x, the additive inverse of f of x, is equal to f of minus x. You're just verifying, because this is saying the additive inverse. This is just a notation for an additive inverse. The additive inverse notation is equal to the formula f of minus x. That's what that is saying. We're going to use that in the next
Ideas that we're looking at. Let F be a homomorphism of a ring A to a ring B. Show that the range of F is a subring of B. I want you guys to try proving this from now on. You use the part 1, the shortcut rule that we have, and try and show that you have a subring here. Talk it out amongst your group. Don't try and do it all by yourself. And the page number for that first part is page 182. Use that stuff from page 182. I can't quite scroll it up all the way, but you can sort of see. Remember, you're using the property f of x. You're going to use that property. You're going to use that.
You do.
Prove that it's a subring.
So that would be close with respect to subtraction.
You have to show close with. So what does it mean to be close with respect to subtraction? So you can have for all A, B, and B, you have to show A minus B is a B. And you have to show A times B. You can call range of F your set B. No, it's not all of your ring B. It doesn't have to be on two. Yeah, it's the range of F is.
Can be a
Yeah.
subset of the So it's just like.
This is equal to all f of x. X is the node.
Oh.
We know
That's pretty much our negative.
f of A equals f of A, f of B.
It's,
The range of F is
it's your
everything.
entire,
Which really
No.
becomes like,
you know, the square
or wherever it goes.
Okay, yeah, yeah.
So we, well, like, the definition of first aid is talking about this will make something a ring, but now
Yeah.
we're trying to use it.
Now we have a shortcut where we only have to prove two things instead of three things.
Which shows a subject.
Which was the subject.
Which is multiplication.
Yep. Does everybody have the number 3 written down? There's the hint that you're gonna be using for number 2. And at page 182 is the thing that we proved first. Middle of page 182. What?
Are we working on
Number 3. You're trying to show you have F takes A to B as a homomorphism. That word never stops. Show that the range of F is a subring of A. I'm sorry, is a subring of B. That's what you're trying to show. Take any two elements and bring out the homomorph columns.
Yeah.
I would call them Y.
why?
No, just Y. Y1 and Y2. Because usually when you use function notation, you have Y equals F of X.
Yeah.
So we're talking about the Y values.
There's no one else
Yeah, so if you have, if Y1 is in the range of F, then there exists an X1 in A such that F of X1 is equal to 1, right? Definition of range.
So, since A is a ring, therefore any element of A goes to additional placement.
Yep. Let's go on. You guys have seen how to prove number 3. We're not going to type that one up. We want to go and look at number 4. This was talking about the kernel as an ideal. What is our definition for an ideal? Yeah.
close with addition negatives.
Yeah, closed with addition, negatives, and
B absorbs products.
absorbs products means multiplication.
Oh.
Okay? So, addition, negatives, and multiplication. We did subtraction and multiplication. It's not quite the same thing.
If you had an ideal and a subring, you just get a ring.
Yeah, you don't necessarily get an ideal back. You have to have both of them have to absorb the products. And it might not. See, the multiplication, the absorb the products, is all the products in outside your ideal, but in the ring containing your ideal, along with your ideal, have to end up in your ideal. So it's kind of like cosets. Ideals are like cosets.
Okay.
But now we have 2 operations on them.
Okay.
Yeah. So let's prove this one. Now, we went through the process of showing closed under multiplication and closed under subtraction for the previous one for subring. You have a couple of subring homework problems. So how do we show closed under addition? Yeah, take any two elements in it. Yeah. So let A and B be in our kernel of F. How about that? I'm trying to remember what we're going to show as our ideal. So let A and B be in the kernel of F. What does that tell you about A and B if it's in the kernel of your function? Yeah, it gets mapped to the neutral element. So then F of A equals to F of B is equal to, what do we want to call our neutral element? 0? I don't want to type. I'm going to type a 0. It's easier to type. And this is 0 for in our set B, the range of F. I don't want to type a delta. I set myself up, didn't I? Okay, so then how do we show that A plus B is in the kernel? Yeah, we have to show that F of A plus B equals to the neutral element, right? To be able to be in the kernel. That's the definition of being in the kernel. So we have to show that F of A plus B is the neutral element. Well, F is a homomorphism, so what does that tell us about F of A plus B? Which equals to 0 plus itself. But what's that equal to? Yep. So what's our conclusion? A plus B is in the kernel of F, and kernel of F is closed under addition. Okay, what's the second thing we have to show? Multiplication? Negatives. So, since we assumed that A was in the kernel of F, we must show that negative A is in the kernel of F. Tell me about, that second proof that I just typed up and showed to you guys. I didn't actually type it up for you guys. But what did that tell us about F of a negative value? Negative F of A, property of homomorphisms. But what is negative F of A equal to? Negative 0. So what does that tell you about negative A? In the kernel of F. It's in the kernel of F. So, thus, kernel of F is closed with respect to negatives. Now what's the last thing we have to do? Absorbs products. And it has to absorb products going both directions, left-hand and right-hand multiplication. So let X be in any element in A. Now this is where we have to plug in our X times A. A is any element in the kernel. Tell me about what the homomorphism says about multiplication. F of X, F of A. But tell me what F of A is, yeah. And what is, when you multiply by the neutral element, you get neutral element.
Wait, when you multiply by the neutral element, don't you get?
It's the neutral element of addition. We showed this when we were talking groups a long time ago. You get the neutral element. Neutral element of addition, when you multiply by it, you get the neutral element. You don't get your number. That would be the neutral element from multiplication. Mhm.
She has a little face.
Actually, we didn't show that a long time ago. They showed that in this chapter, in chapter 17, I think. Mhm.
It's the neutral element. The neutral element of addition.
Yeah. Multiplication, it gives you the, yeah. Mhm. This, I think, was shown in chapter 17. You know, this is actually something that has shown up on a test question before. That was an old test question. No, it's what happened, whatever I find highly entertaining when I'm reading through my notes.
He made a good joke during it.
This is true, he did. I'm likely it's not to remember that part because it didn't get typed up. Yeah, I don't listen to the recordings. It would take forever. And then we actually have to check the other direction. Oh, before we do that, this tells us that XA is in the kernel of F, right? So go the other direction on it. You have F of AX. What should we do? F of A, F of X. But what is that equal to? 0, F of X. But what is that equal to? 0. Thus, what do I know about AX? Kernel of F. And so, kernel of F absorbs products. We have to check it both directions before we can say it absorbs products. Draw your big conclusion. Kernel of F is an ideal of of A. Yeah, I couldn't remember where F went. It goes from A to B. It's an ideal of A. And that verified the last thing that they didn't approve in the section.
So ideally, that's how you want proofs done.
Ideally, yes. Yes, indeed. Okay, we are done for today.